Hi, so in this video, we will learn about Kepler's laws. Let us begin. The objective here is to explain Kepler's first, second, and third laws of planetary motion. Newton has three laws of motion. Similarly, we have Kepler's three laws of planetary motion. Kepler's first law, Kepler's second law, and Kepler's third law. Let us start. Here are some keywords for this video. The first is ellipse. As you can see, ellipse is a shape like egg shape, like circle. Ellipse is, like circle is a shape, triangle, square is a shape. Similarly, ellipse is also a shape. Focus, then the plural form of focus is foci or foci. Foci or foci. Both way you can pronunciate this word. Now, other word semi. Semi usually meaning half, major, big, minor, small. So let us talk about ellipse. What is ellipse? Ellipse. So I have put the word oval for ellipse. So it is a shape. It's a 2D shape, two-dimensional shape, and it has two foci. It has two foci, as you can see, this one here and another one here, F1 and F2. For, this is similar to center of a circle. A circle has one center, but an ellipse has two foci. We will not call it center, we will call it focus or foci. Now, from here to this, the distance is, we can say, semi-major axis, and this one is semi-minor axis. Now, Kepler's first law of planetary motion. What is Kepler's first law? So, Kepler's first law is about the shape of the path of a planet around the sun. How planet move around the sun, in which path, in which shape of the orbit. So this first law only tells about the shape of the orbit. The orbit of every planet is an ellipse with the sun at one focus. So every planet around the sun, they move in a elliptical path, not the circular path. The path is ellipse, not circle. As you can see in this diagram, this is not a circle, this is an ellipse. And as you know, the ellipse has two foci, one foci here and the other foci here. One focus here and other focus here. So sun will be at one of the focus, one of the foci. Sun will be here. What will be here? Here will be nothing, only focus. Focus 2. You can see the green color here. This is a planet. It can be the Earth, can be Mars, Mercury, Jupiter, anything. I ask my students sometimes, what is here? So I get sometimes, some students, they say, here is another planet. No, it's wrong. He, There is nothing here, only the focus, only the point, the position, nothing here. Only here the sun will be there, and the planet will be on this path, on this path, on this orbit, on this orbit, which is ellipse in shape. So here nothing, no mass is here. So this is Kepler's first law. Kepler's first law tells that the shape of the orbit of a planet around the sun is an ellipse, and the sun is at one focus. Let's move to the next, which is second law, Kepler's second law. Why we call it law of planetary motion? Because these all three laws are related with the motion of the planet. Now, second law. Second law, let me read first what second law says. A line joining a planet and the sun sweeps out equal areas in equal time. This is the second law statement. Now I will explain. So, draw, uh, draw a line from the sun to the planet. This is the planet, this is the sun. Draw a line. This is, of course, not a real line, imaginary line. So we draw a line here, for example. Now, after some time, for example, let us suppose after 30 days, this planet travels from here to here, from this point of the orbit to here in 30 days. So initially the line was here, but the line is also moving because the planet is moving, the line is moving. So we can say we can have here the area. You can see this area, right? Areas, made by the line. You can see here this area as I'm highlighting this area. This area, this whole area, and that looks like triangle area. Okay, so this area covered by the line in 30 days. Now, the same planet, when it is here, in 30 days, next 30 days, it comes here. Now, again, we have lines, moving. The line is moving with the planet. So, this 30 days, this is the area, area 2. You can see area 2. Okay. Sorry, this is extra. Should I erase? So this area is area 2 and this area is area 1. So Kepler says that these two area will be equal. See this equal area, this equal area, these will be equal areas because the time of sweeping was equal. Here 30 days and here also 30 days. So this is the second law of planetary motion. I repeat, the line joining a planet and the sun, which is an imaginary line, not the real line, sweeps, which is cover equal areas in equal time. This is Kepler's second law. Now let's go to the third law. Kepler's third law of planetary motion is this formula. If we remember this formula is Kepler's third law. Or this. So this is a square of the time period, square of the time period, or square of the orbital period, equal cube cube of semi-major axis, which is equal. Both are equal. Square of the period equal to the cube of the semi-major axis is equal. This is for a planet. I mean, see, this time period will be the time taken by the planet to complete one rotation, one revolution around the sun. See, the planet is here, and this uh, revolves around the sun, completes one, here, reaches here again. This is the time is T, which we call period of a planet, or time period of a planet, or orbital period of a planet. We have different names. Period, simply we can say period of a planet. So when we call period of a planet, it means the time to complete one revolution around the sun. Example, for the earth, this T will be 365 days. The time period or the period of the earth is 365 days, because earth takes 1 year or 365 days to complete one revolution around the sun. And this is the semi-major axis. As you can see, the dotted line from here to here, semi-major axis, which is denoted by R. So this formula is Kepler's third law. It says the square of the period of a planet is equal to cube of the semi-major axis, always. This formula holds true always. And the same formula we can generalize for two planets also. If we have two planets, planet 1 has period T1, planet 2 has period T2, planet 1 has semi-major axis R1, and planet 2 has semi-major axis R2. So you see, square here, cube, cube. So this is for the two planets around the sun. So this is Kepler's third law. Now I have written here what is T, what is T1, what is T2. This is a picture. You can see the sun here, one planet here, another planet here. This distance will be R1, this will be R2, because this is for planet 2, this is for planet 1. Now, in our most of the calculations, we will consider this R1 as a distance between the planet and the sun. It will be similar actually. You know, if we go back to the picture, semi-major axis, it is, the distance almost average, because the planet keeps on revolving in an ellipse path, which is not a circle, right? So the distance between the planet and the sun keeps on changing. See, right now the distance is this much. When the planet comes here, the distance is bigger, longer. When the planet comes here, the distance will be shorter. That's why we take this semi-major axis R, which is average of all the distances throughout the year, throughout the period of the planet. So this R is usually the distance between the planet and the sun. Now, Kepler's laws are valid for satellites as well, moons as well, comets also. Now, what is AU? AU is astronomical unit. This is the distance actually. It's a long distance, very long distance. This is the average distance between Earth and the Sun. Why we use this word average here? Because as I explained before, the Earth and the Sun, the distance between them is not fixed. It keeps on changing. It keeps on changing. every day of the year. So that's why this is average. So 1 AU is a very, very huge distance, which is 1.5 times 10 to the power 11 meter. Now let us talk about comets. Comets are some objects in space made of ice and dust, which has a tail of gas and dust. And when it gets close to the sun, we see, the tail. When it comes close to the sun, you can see this, tail. So they are made of ice and dust. Okay. Comets are of two types. One which has period less than 200 years, the other which has period greater than 200 years. It means short period comets, they take less than 200 years around the sun to complete one round of the sun. Example is Halley's comet, and the second type is long period. They take more than 200 years around the sun. One example is Hale-Bopp's comet. Thanks for watching.